So let's just review the Bohr atom with, we typically are just interested in the hydrogen atom because that's what it describes reasonably well. But once we get to more complicated atoms, there do tend to be some problems because it's not a perfect description of the atom, and we will get to a better description of the atom, but it's a pretty good one. And let's just remember that for the hydrogen atom, we have a single proton, a single neutron in the nucleus, and a single electron. And for the higher number of protons, right, the charge of the nucleus is Ze, and the charge of an electron is E, the magnitude of the charge. And of course, the E is 1.6 times 10 to the minus 19 coulombs, so that the charge of the electron is minus E, and the charge of the nucleus is Ze. Okay, make sure we understood that. Okay. Wrote down, when we did the derivations for the Bohr atom, we had the energy Ke plus Pe is equal to 1/2 mv squared plus Ke squared, because it was Ze times E for a single electron atom with a nucleus of charge Ze over R squared, over R, I keep doing that. The energy is that, minus, okay. And we just said for the hydrogen atom, Z is 1, and we did the derivation for the hydrogen atom. And we also saw that the force, the Coulomb force, KQQ over R squared, or KZe E over R squared, equals the centripetal force, mv squared over R. And then we derived everything for Z equals 1. Well, if Z is not equal 1, what is the result? Easy enough to do. So with leaving the Z in there for hydrogen, helium, lithium, beryllium, etc., we find that Rn equals n squared, A0. I can't remember if I defined A0 before, but we can just define that here. It's the Bohr radius. It's that Z equals 1, N equals 1, the Z equals 1, N equals 1 radius, smallest radius in the hydrogen atom. That was 0.529 angstroms. Find that the energies, E sub n, the energy levels, are minus 13.6 eV times Z squared over N squared for the higher number of proton atoms. And we find that the Rydberg equation, or whatever we call that, the wavelengths or the frequencies of the emission spectra are going to be Z squared times the Rydberg constant times 1 over N1 squared minus 1 over N2 squared, whatever, when an electron in a higher number, in an atom with higher number of protons, Z is not 1, and this just talks about when an electron moves between two energy levels, N1 and N2. These are the emission spectra, the wavelengths of the emitted light if we're going from a higher energy to a lower energy. Just a summary of the Bohr atom. We could do some plugins if we wanted, but I'm not entirely sure how useful that's going to be. We already figured out what the Bohr radius is, looked at some energy levels. We just haven't done it for higher orders of Z, and that's okay. Maybe we won't do that at this moment. So we're getting to the end of chapter 4, where we will discuss the successes and the failures of the Bohr atom and the conformations of the Bohr atom, and we'll find that the Bohr atom is not the correct description of the atom. But the correct description of the atom cannot be understood until we understand the next chapter, which is about waves, right? We've already done some waves, but now we're going to talk about the wave nature of matter, and then we'll be able to bring it all together with the next chapter. But before I do that, I just want to do a demo.